Oh, still preparing the stream. Okay, we're good.
Hello, everybody. Hope you're having a wonderful week. Let's start off our presentation today. All right. So, hello, everyone. Welcome to Space Place Canada's exclusive event and expert-guided discussion, Astronomy Meets the Stratosphere, Balloon-borne Telescopes. As you may have heard, in April of 2023, half-meter or 20-inch superpressure balloon-borne imaging telescope, also known as SuperBIT, flew from Wanaka, New Zealand, to conduct imaging of celestial objects from the stratosphere, circling the globe 5.5 times. Our incredible speaker today, Emaad Paracha, is an astrophysicist at U of T, and he wrote on his X account, "Proud to share that I helped launch one of the highest resolution telescopes in the world, SuperBIT, in collaboration with NASA, U of T, Princeton, and Durham University from Wanaka, New Zealand. SuperBIT flew around the world in 40 days from around 110,000 feet, 3 times as high as planes. So today, we're very lucky to have Emaad here to share his knowledge with us. We will chat and network throughout our time together, and there will be lots of time for questions after the presentation. So keep your questions ready. As always, we'll be very grateful for your active participation. Before we begin, I would like to acknowledge and pay respect to the traditional land and indigenous peoples on whose ancestral territory I and some of you are located on today, in Hamilton, Ontario, Canada. The city of Hamilton is situated upon the traditional territories of the Erie, Neutral, Huron-Wendat, Haudenosaunee, and Mississaugas. This land is covered by the Dish with One Spoon Wampum Belt Covenant, which was an agreement between the Haudenosaunee and Anishinaabeg to share and care for the resources around the Great Lakes. We further acknowledge that this land is covered by the Between the Lakes Purchase, 1792, between the Crown and the Mississaugas of the Credit First Nation. Today, the city of Hamilton is home to many Indigenous peoples from across Turtle Island, and we recognize that we must do more to learn about the rich history of this land so that we can better understand our role as residents, neighbors, partners, and caretakers. Many of you are joining from different parts of Canada or maybe from other countries, and may wish to familiarize yourself with the histories and stories of the land and Indigenous peoples on which you live. So, for today's talk, I'd like to start out by telling you about Space Place Planetarium Canada, also known simply as Space Place. Space Place is a Canadian charity comprised of a multidisciplinary group of professionals determined to bring an iconic physical public planetarium back to Toronto. By the way, we add the word iconic, meaning large. There are other planetariums, they're just portable and small. Space Place is also currently supporting a virtual planetarium for Canada and the world as of now. Not everybody knows this, but up until 1995, Toronto used to have a world-class iconic public planetarium. Toronto is now the largest international city without one. It is a critical missing piece of Toronto's tourism and educational infrastructure, and we want to bring the big planetarium experience back. I would encourage all our participants today to get involved in Space Place. Check out our website, spaceplacecanada.ca, often to make sure you don't miss what's new, especially to stay in the know about the upcoming solar eclipse and how to get your hands on our new eclipse glasses. More details and events about that coming soon. You can also email us to inquire about our work. Be a volunteer or apply to be a member. We are engaged in advocacy and planning, recruitment, events, and fundraising. We are even currently looking for help on assessment of our new potential location at the Atrium on Bay in Toronto. So if you're looking to get involved, there is an area for you, and we would love to have you join our team. So, I'm Sky, and I'll be your host for this event. And we also have Matthew Simone producing behind the scenes, monitoring our comments and questions on YouTube and making sure that our Zoom call runs smoothly. So thank you, Matthew. As we go along, feel free to drop your comments in the chat box. Now, just to get things started, please tell us where you're tuning in from tonight and tell us all one thing you hope to gain by the end of this event. For me, I had the privilege of working with our speaker Emaad at U of T in the summer of 2021. With COVID-19 still at a fever pitch, so to speak, I was first of all excited to be able to even be there, but I was so thrilled to be able to contribute a small part to the SuperBIT project with a solar array design, as well as one of the circuits for the flight computer module, under the guidance of Dr. Bart Netterfield. That summer experience further built up my passion for space and brought me to where I am today, a fourth-year engineering student at McMaster University, a proud space nerd and fan of all things astronaut. Please share with everybody, anybody who's attending, what moments shaped your interest in space. As we go along and talk, just feel free to share your thoughts in the chat. Now, before we go on with our speaker, just to tell you a little bit more about our community again, Space Place is a Canadian charity made up of a multidisciplinary group of volunteer professionals determined to bring the iconic 21st century public planetarium back to Toronto and supporting a virtual planetarium for Canada and the world. Our mission reflects 4 points: to serve the local community, educational, and tourism needs, to promote awareness of Canadian space-related earth sciences, STEAM successes and opportunities, promote online curriculum-based STEAM program opportunities and activities for underserved communities, and spotlight educational prerequisites for employment prospects in space and on Earth in various occupations in all our programming. Also, Space Place Canada has more than 10,000 supporters worldwide, mainly through social media and an active events program. A recent Nanos poll showed that Ontarians recognize the need for Space Place Canada and its contributions to education, tourism, and research. We're able to host amazing events like these, greatly due to our sponsors. And I'd also like to kick things off by thanking our Jupiter sponsors, which are MDA, as well as Larson and Toubro Technology Services. And with that in mind, we'd like to share a brief message from MDA. To conclude our sponsors, we also have Pratt & Whitney, which is a Mars level sponsor, as well as two Mercury level sponsors, which are Global Public Affairs and Stradia. Thanks again to all of our sponsors for your continued valuable support of Space Place Planetarium Canada. Now, we have many more events and outreach initiatives lined up for the year, and this means that you can help us make them happen. You can help us reach our goal. It's a very exciting time for Space Place. As I mentioned before, we are currently looking for help on assessment of our potential new location at the Atrium on Bay in Toronto. We could also use your help to fund it. Please consider a donation to Space Place. Check our website, spaceplacecanada.ca, for details. With a donation of $40 and your home mailing address, we will send you our awesome and unique planetarium music card, which enables you to download the music from the McLaughlin Planetarium, which, believe it or not, closed in 1995. Download the music, take it outside, look up at the stars, and enjoy your homemade planetarium experience. At the $75 donation level and your mailing address anywhere in North America, you will also get a copy of An Earthling's Guide to Outer Space by Bob McDonald of CBC's Quirks and Quarks. Please email us at info@spaceplacecanada.ca if you'd like to apply to be a member or to volunteer with us. Now, without further ado, let's all focus on our mission parameters today. We have an absolutely incredible speaker here with us. Emaad Paracha is a PhD candidate at the University of Toronto, studying physics with a specialization in astrophysics, and a researcher with the Balloon Astrophysics Group, helping design, build, and launch balloon-borne telescopes. As I mentioned before, he was a key member of the team behind the successful flight of the superpressure balloon-borne imaging telescope, or SuperBIT, in 2023, a diffraction-limited near-space telescope that was launched by NASA from New Zealand and flew for 40 days at an altitude of 33 kilometers, imaging several galaxy clusters to help map the distribution of dark matter around them using weak lensing. Emaad is an avid space and technology enthusiast, aiming to solve critical problems in space technology, from enhancing communications and edge computing to pioneering innovative software and hardware designs in space. Believe it or not, Emaad also had some free time and maintains a totally awesome photography project called the Currency Project, where he photographs iconic landmarks featured on global currency. Coming soon is a selfie with the Canadian $5 bills Canadarm. Go, Emaad! That's dedication. As I mentioned before, we will have question time after Emaad speaks. So please save your great questions for him for after the talk so that he can give the questions his full attention and they won't get missed in the chat box. So over to you, Emaad.
Thanks, Sky. Thanks so much for the very cool introduction. I probably couldn't have done a better job myself, but no, thank you very much. And I'll share my screen just so I have the presentation up, and then I can do the introduction as well. And I hope everyone can see my screen. I think it should be good, right, Sky? Okay, perfect. All right. So I didn't know actually before this that I would also be talking about my currency project, although I can talk about it afterwards. But the primary subject of today is astronomy from the stratosphere. And that is actually something that Sky has dabbled in as well, as part of a summer project. But I'll talk more about SuperBIT and balloon-borne telescopes in general, and how and why we're doing astronomy from the stratosphere. All right, so a little bit about myself. This goes to the next slide. So I'm currently a PhD candidate at the University of Toronto. We're doing my PhD in physics, but I'm specializing in astrophysics. And the University of Toronto is in Toronto, Canada. So the collaborators of the SuperBIT team are professors, postdocs, and also PhD students, and also other graduate and undergraduate students from the University of Toronto, Princeton University, and Durham University in the United Kingdom, plus also people from NASA JPL, the Jet Propulsion Lab, with postdocs and professors over there. So we have people on our team, on the SuperBIT team, ranging from graduate students to postgraduates to even professors. And this is a picture of the SuperBIT team right here. Let me actually just make this a little bit better, because I'm trying to figure out where I am in relation. I'm trying this new cool thing where I'm on this little map. But the SuperBIT team is pictured right here. We have a lot of people over here from around the world, and there's SuperBIT behind us. And this picture was taken in New Zealand. There's also ex-students who worked on SuperBIT as well, students who have graduated, and also students who were just there for summer projects like Sky. And that's something we'll talk about in just a bit as well. So this is another little cool thing. So SuperBIT is a project that is essentially built, and if I go back, we have collaborators from the University of Toronto, from Princeton University, Durham University, who are all building this together. But then I would be amiss to say that we do get a lot of help from NASA and the Canadian Space Agency, but also primarily NASA. And NASA was responsible for helping launch us. And this picture right here is actually with the NASA Administrator Bill Nelson and the Deputy Administrator Pamela Melroy in Wanaka, New Zealand. And this was earlier in March of last year, where they actually came down to New Zealand and Australia to visit the space agencies over there, and they actually paid us. And SuperBIT, this is SuperBIT about a month before its flight. They paid us a visit. So what is balloon-borne astronomy? What do you mean by balloon? What do I mean by balloon? Is that just birthday balloons? So honestly, kind of. And this is where it gets interesting. So this is not a hot air balloon, which is open. This is actually a sealed balloon, like you would expect a birthday balloon to be. But the main difference here is that birthday balloons they range from 0.25 to about 0.5 cubic feet of helium, while the balloons that we actually travel on, what we actually send our telescopes on, are 40 million cubic feet of helium. So these are balloons that, when they're fully inflated, a small football stadium can actually fit inside of the balloon. So these are massive balloons, and they're rated to stay up for about 100 days, and they fly at about 40,000 meters. About 40,000 meters, or 110 to 120,000 feet. Now, normal commercial airlines, they fly between 30 and 40,000 feet. These go up to 110, sometimes even 120, but usually around 110,000 feet. So 3 to 4 times as high as planes fly. So we're way up there. And that is above 99.7% of the atmosphere. And that number is crucial. Why? Because that actually allows us to be above any sort of atmospheric pollution, any thermal or light pollution. We're not affected by any of those. We are above the atmosphere, and we can actually get diffraction limited imaging. And the launch day is usually around 12 to 15 hours long. If you compare us to sort of a launch that you would have of a telescope on a rocket, we're roughly, similar, but obviously a lot of planning goes in. So a lot of planning goes into either of them. Our launch day for a balloon is about 12 to 15 hour long, and that includes 3 to 4 hours of just filling time. So if you take a birthday balloon, you could fill that up in less than a minute or less than 30 seconds. But these balloons, you need a lot of time. This is just another little. This is another infographic, and this is actually coming from NASA, just showcasing more about the balloon. So the balloon is actually nicknamed the pumpkin, and that is because it takes on a little pumpkin shape when it is fully inflated. So when it is inflated on the ground, it is inflated about 1% of at actual volume with helium, but then as it goes up in the atmosphere, the helium expands because the air pressure is very low, up at 110,000 feet. And that is where the balloon actually expands to this pumpkin shape. And if you look at this infographic right here on the right side, you'll see that from the top of the balloon all the way down to where SuperBIT or any other experiment is, It's as high as the Washington Monument, or even the Statue of Liberty, which is shorter than the Washington Monument. So NASA does these launches from several sites around the world. Some of the primary ones are, there's one also in Canada that the Canadian Space Agency and CNES also do. CNES is the French space agency. They do it from New Zealand, and they also do it from Antarctica for several missions that are day-only missions. But we launch from New Zealand, and I'll talk more about our flight and our launch and our science case as well. And then this is just how they actually fill up the balloon. So it's not a simple helium, it's not just a small helium canister with a small pump that you're filling up a balloon with, that you fill up a birthday balloon with. If you see in the back, you'll see that there's these truckloads of helium that are there to actually fill up the balloons, and they fill them up using these long pipes that go up to the balloon, and they actually fill up two balloons. So there's a tow balloon, which is on top, and then there's the actual balloon. And the tow balloon's purpose is to actually hold up the balloon to ensure that it actually comes up and doesn't fall to the side. And if you've seen a Goodyear blimp, 195 Goodyear blimps can actually fit inside one of these balloons when it is fully inflated. So these are truly massive balloons that we build telescopes for, and the telescopes are attached on top to them. And this is a quick little video showing the launch. And this was SuperBIT when it was fully inflated, up at about 100,000 feet. And that was the day of the launch. It was we started at about 12. Actually, before that, we started at about 11 p.m. New Zealand time, and this is about 11 a.m. New Zealand time when it actually launched. So just talking a bit more about the balloon, if you've ever seen an airplane in the sky from the ground, that's what it looks like if you just see it visually. So, or if you even take a picture with your phone, that's what you'll see for a plane that's flying about 30,000 to 40,000 feet. You would actually see the balloon at about the same apparent size in the sky. But the balloon is actually flying 3 to 4 times higher than the airplane. So that actually shows the scale of the balloon itself and how massive it is. And this is actually a picture of SuperBIT. So there's tiny little SuperBIT flying, and this was from the ground in Chile a few days after launch. So there were people in Chile who actually took a picture of this. And the balloon is about 100,000 feet at this time, which is 3 times as high as commercial airplanes. And like I mentioned before, the balloon is actually inflated about 1% at launch, and then it expands, the helium inside, it expands the balloon when it gets to float at 110,000 feet. And that is what the balloon looks like as it launches. And this is closer to the ground. All right, so this is another image of what it looks like when we're up there. So as you can see, we're above the atmosphere. There's no more blue sky. If you're on a plane and you're at 30,000 feet and it's day, you still see blue, which means you're still, we are still within a good chunk of the atmosphere. Versus over here, you're well above the atmosphere. You're well above 99.7% of the atmosphere. And this is where there's a very nice sweet spot for putting up a telescope, if you can build one. So here's where we talk about the experiment, where we talk about SuperBIT. So this is what I helped build, and this is what all the different universities collaborated together, what my professor collaborated together, and this is the main focus of my PhD project. So SuperBIT, or super pressure balloon-borne imaging telescope, It was jointly developed by U of T, Princeton University, Durham University, with assistance from NASA JPL. And this was funded primarily by NASA and the Canadian Space Agency. So this project actually started in 2014 before I even joined the project group. But it was started by my professor in collaboration with the professors from Princeton and Durham universities and other collaborators from NASA JPL. And they did 4 test flights before we actually did the science flight last year. And there were 2 in Canada, so one in 2015, one in 2019. Those were engineering test flights. Those were with CNES and the Canadian Space Agency. CNES is, again, the French space agency. And there were 2 in Texas in 2016 and 2018 that were done with NASA. And all of that culminated in a science flight in 2023 from New Zealand. So all of those were engineering test flights, and also one test flight that was an engineering plus science test flight to actually show that we can achieve the stability that we require. So a bit more about SuperBIT, and then I'll go more into the technical details about the stabilization. So like I mentioned, SuperBIT is attached to the bottom of that balloon. Now the balloon is up here. There's a big distance. I think it's about 300 or so feet, or way more than that. And then SuperBIT is at the bottom of that, tethered to the balloon. And it is over there imaging different galaxy clusters. So it is a 0.5 meter modified Dal-Kirkham telescope with 0.05 arcsecond stability. And I'll talk more about that afterwards as well. Like I mentioned, it is above 99.7% of Earth's atmosphere, which allows for diffraction limited imaging in space-like conditions, but we're doing it for a fraction of the cost of similar space-based telescopes. And that's why we do it on a balloon, because we don't have to send it up on a rocket and spend that much money to create something that goes in orbit. Instead, we can send it up in a balloon and still achieve diffraction limited imaging in a space-like environment. There were communications links that we used, including Starlink, and other communications, including Iridium Pilot and TDRS and more. And I'll talk more about that as well. And our main science focus, or our main science goals, were actually on weak lensing observations. And I'll talk about that as well. We launched on 16th April 2023 from Wanaka, New Zealand, which is in the South Island of New Zealand, about 1 hour north of Queenstown, if people have heard of Queenstown. And it landed in Argentina in Patagonia, in the Patagonian desert on 25th May 2023. So it was about a 40-day flight that we had. So more about the stabilization. And all of you might be wondering, if you have a telescope up in the stratosphere that's attached to a balloon, how do you actually keep it stable? You do get the space-like conditions, which is wonderful. You don't have the atmosphere, you don't have any sort of pollution to worry about, but you have a telescope that's dangling, essentially. So how do we make it stable? We were able to achieve 0.05 arcsecond stability for 5 minutes, which is how long we took an image. Each image was about a 5-minute exposure time. And just to give you a sense of what an arcsecond is, 1 arcsecond, if you don't know, is the size of a coin from 4 kilometers away. So if you're holding up a coin, if somebody's holding up a coin and standing about 4 kilometers away, that size of a coin is how big 1 arcsecond is. And we were able to achieve 1/20th of an arcsecond stability. So just imagine if you have a needle, or for people in Canada, imagine if you're standing if you're standing on the Toronto Islands and you're trying to thread a needle through the top of the CN Tower. Or for people who are not in Toronto, imagine you have a needle and you're trying to thread it from 2 kilometers away, and you have to make sure you hold the thread steady enough so that you don't touch the sides for about 5 minutes. That's how stable we were able to get there. And the way we were able to do that, and I'll show some more diagrams as well, is we actually had 2 cameras on the telescope for raw stabilization, and then 2 further star cameras for sub-arcsecond stability. And those were actually at the focal plane. So if I go further, there's different axes that we have to stabilize. One is roll, so telescope essentially moving side to side. Pitch, the telescope itself moving up and down. And then yaw, as well. So we had two cameras. One was actually pointed in the same direction. It was actually attached to the telescope itself. It was pointing in the same direction as the telescope, and the other one was pointing orthogonal to that. So if you look over here, there's if you draw a 90-degree angle over here, it's looking to the side. So what those cameras actually did, they used to track stars. So they would lock on different stars. They would essentially lock on a star and track its movement as the telescope was imaging. We used to image galaxy clusters. So as it was imaging galaxy clusters, we used to track different stars. And now as soon as the star would move a certain amount, that was then relayed back to the motors that are moving the different axes. So we have one motor in yaw, we had two motors for pitch and two motors for roll as well. As soon as actually we had two motors for yaw as well. We had a reaction wheel at the bottom and a pivot at the top. As soon as any change was observed in either direction, whether sideways or straight, if there was any change in the stars, wherever they moved, that was relayed to the motors, and the motors corrected for that. Now that gets us to about an arc second, but to actually go down to sub-arc second stability, we had another set of star tracking cameras, the focal plane star tracking cameras. And those were above and below essentially our effective focal plane. Now what they did was they locked onto one of them, and every exposure used to also lock onto a star. And now this is essentially our optical assembly. We're two mirror telescopes, so the light comes in. It's the M1, the primary mirror, then the secondary mirror, and then it goes to piezoelectric tip tilt mirror, and then it goes to our science camera. Now these star tracking cameras, one of these would lock onto a star, and again the same algorithm. It would track where the star is and how much it is moving. It would relay that information back to the tip tilt mirror, which would then adjust to factor in those changes as well. And that's how we were able to achieve sub-arc second stability up in the stratosphere for about 5 minutes. So there's a lot of technology going into this just to achieve the stability. And that was the reason why there were so many test flights that we did beforehand to ensure that we can actually achieve that sub-arc second stability and make this project worthwhile. So this is a video that I'll quickly show. This was actually in our lab at the University of Toronto. And this shows when we moved the actual gondola itself, how the telescope, in this here, we have a door, or a window, I should say, but it's not really a window, it's open air. We have a door at our lab that opens up, and we can actually lock onto a star. So this telescope is locked onto a star, and you can see while the gondola is moving, the telescope itself is not. Yeah, so that's it's a small demonstration. I wish I had a video of it up in the stratosphere locking onto a star and actually moving. Fortunately, I was not able to get that, but this is a quick little test that we did. So that's one set of technology that we had to use. Then there's also communications. So how did we communicate with SuperBIT? So there were different sets of communications that we used. One was Starlink, which was used for the first time on any balloon mission in the world. So this was the very first time that we did. You can actually see the Starlink router right here. This is our whole antenna boom with different antennas, GPS receivers, and other pieces of communications equipment that we used and also NASA used. So this was used for the first time. Starlink was used for the first time, and this actually gave us nearly 3 Mbps to more than 60 Mbps connectivity, even over the Pacific Ocean and the Atlantic and the Indian Oceans. So this was insane. However, unfortunately, this was the first time we were doing this, and this was a test for Starlink as well. So we did not have the right equipment at that time, and we didn't know if it was rated or not. So unfortunately, due to some reason, which we're still investigating, it did fail after 10 days. But we still had some backup, which was used in the previous balloon mission. So there was TDRS, which is a U.S. military satellite network, but they also have bandwidth for scientific missions. And that works for up to 200 Mbps, but that's just military. We only got 100 kbps to 1 Mbps. And then we also used Pilot, Iridium Pilot, which is another commercial satellite communications device. It's built for ships. It is, I believe, end of life now, but it gives about 25 kbps, but it is very spotty. We sent commands over Iridium, essentially text messages that we sent to the telescope to move it around or do things. There were also, we used to downlink files using first Starlink, but then after that, we had a whole system of downlinking files, and we created a method to capture missing packets to see if there's any missing packets, because as we're transmitting data, data is unshielded by cosmic rays. So one cosmic ray can corrupt a packet. So we used to check for those and re-request packets as well. And we also downlink using data drop modules, which I'll talk about in just a little bit as well. So what is our research? Why did we do this? What we wanted to do was to image galaxy clusters for gravitational lensing. So gravitational lensing is the bending of light due to mass that is present in the light's path. So if I quickly look at this diagram right here, and this is actually a galaxy cluster, because of a large amount of mass that may be present between us and a galaxy that we may be looking at. So imagine us over here at this point in front of this blue image. And there's a big galaxy cluster, and then there's also these scattered galaxies in the back as well. If you view these set of galaxies from this side, on the other side of this blue rectangle, you would see galaxies in their actual shape as they are. However, on this side, because there's this massive mass between us and the set of galaxies on the other side, that massive mass is bending space-time. And therefore, the light, as it is coming to us, is also being bent. And that causes lensing. So that causes distortions in how the masses look, or how those galaxies look to us as we're observing them. And as you can see, even though their intrinsic shapes look like this, we would be seeing them in a different way. We would be seeing them orientated in a different way. And that is because of the mass that is present in those galaxy clusters. So galaxy clusters and big galaxies can bend space-time, and thus they bend the light that is coming from behind them to us as well. And this can be often in the shape of big circles or arcs. So there's that's called strong lensing. And you can see that over here. This is a very, very extreme case of strong lensing, where the source, where the galaxy that is being lensed is right behind this big galaxy. And when it is right behind this big galaxy, it's sheared to a big extent, and you can actually see these arcs. And this looks pretty cool when you see it. And this is called strong lensing. But what we were after was weak lensing, which is very little changes. But you see lots of different galaxies. As you can see in this case, you see lots of different galaxies that are slightly distorted. So you can figure out the mass profile of general areas. And what that actually helps us do is map out dark matter in galaxy clusters. So we estimate that about 80 to 85% of galaxy cluster mass is actually dark matter. And that is because dark matter first came together and created these hotspots for regular matter to clump together and create these galaxy clusters. So in any given galaxy cluster, 80 to 85% of the mass is actually dark matter. So we cannot see it, but we can see its effect on regular matter gravitationally. And by seeing how much these galaxies that are in the background, they get lensed, we can actually detect areas of higher concentration of dark matter or lower concentration of dark matter. And we can see that within the galaxy cluster as well. And that can then help us create a better model for our universe, better cosmological model for our universe. So just again, a little bit more on this. So there's a big galaxy cluster. Again, galaxy cluster by itself, 80 to 85, 15% of 15 to 20% of the mass of a galaxy cluster is the galaxies itself. But then 80 to 85% of it is dark matter. And we see that in its effect in the light that we see bent of the different galaxies that are in the back. So this is actually strong lensing, case of strong lensing, but it applies to weak lensing as well. sets of galaxies. We see their light. We see their light is bent when it comes to us, and these are the distorted light rays that we study, and we create maps of areas of higher dark matter. So these are again examples of strong lensing. You can see that over here. This is a Bell 2218. This is a galaxy cluster. These both were taken by Hubble, and you can see these areas of strong lensing with galaxy shapes extremely distorted, and you see these streaks. This is a very cool one. This was actually a star, a quasar, that was imaged, and this is actually one. However, because it's directly behind this big mass, you actually see 4 instances of it, just because of how it is lensed. So there's 1, 2, 3, 4. I believe there may be also a 5th one, which is embedded in this actual mass, but you see 5 different instances of the same object because of strong lensing. But then here's an image that we took for Bell 1689. This is again a big galaxy cluster. You'll see a lot of galaxies. This is an example of weak lensing, where you can't really tell just by your eye, but because there are many galaxies in the background that are distorted by a certain amount, you can use statistical methods to actually recover how much they have changed. Because if you look at just one galaxy, if you look at this galaxy, for example, right here, this super small one, you can't tell if it is distorted or not. But if there's other galaxies that are also sort of aligned, and if I go back here, if there's other galaxies that are aligned in the same way, we can recover and see, okay, so there's this specific additive or multiplicative effect that's on them. And we don't know what that effect is. It may be a combination of everything, but there's a certain effect that's on all of these galaxies, and that is due to the dark matter. And therefore, their intrinsic shapes, even though they look like this, to us, they look like this. And we can recover that and create profiles of dark matter. And that is what our research is. And that is what we're currently trying to do. And what that helps us do is create maps of where there's higher concentration of dark matter, where there's lower concentration of dark matter. And in turn, we can use that to test other theories and to refine our understanding of our universe and to refine the standard model of cosmology that we currently work with. So that's more on our science case. Now about our flight. So we launched from Wanaka, New Zealand on April 16th at about 11:42 a.m. New Zealand time. So you can see on the map, this is where we launched from, and this is actually a full map of our flight path. We flew for about 40 days, mostly over the oceans, but we did briefly go over Chile and Argentina. The good thing of doing an experiment with NASA, such an experiment with NASA, is that we worry about building the actual telescope and they worry about the logistics and the political side of getting permission from all these different countries. And they did a good job at that from all these countries that we would be flying over. And they also did the job of actually being responsible for building the balloon, making sure the balloon was tested as well, and making sure the balloon was healthy and monitoring the balloon as well. So the balloon, like I said, is rated for about 100 days, and it was healthy, but it was forecasted to unfortunately go over Antarctica. And this is about the end of May, early June, when there is no light in Antarctica. It is just night because it is winter. So we would get amazing images, but unfortunately, we would not be able to charge our telescope. So NASA made a decision to terminate over Argentina, so we could actually recover the telescope before it goes over Antarctica, and then we'd have to go to Antarctica in December to recover the telescope, and a lot of things may be damaged by then because we can't just go in the dark. So they made a decision to terminate over Argentina. However, we did fly. We did go around the world 5 times, although we didn't go around the equator. We went around this path, but we still did go around the world or around Antarctica. Again, mostly over the oceans and only Chile and Argentina. And then eventually it was over here. And this was very interesting at it was about 10 p.m. on a Wednesday night where we got a message saying, hey, by the way, emergency meeting, everybody come on. It came on at 10 p.m. and they said, tomorrow morning, we're going to be terminating the flight and it is going to be landing over Argentina. And by that Saturday, I was on a flight to Argentina, which was very cool. We did have issues recovering the full payload, and I'll talk more about that. But the hard drives were recovered with the data, and we got all of our data back that we took. And this is again another image of the flight map, just with sort of a flat map projection, and you can see this is our trajectory. So we followed the winds, the trade winds that flow west to east, and as you can see, it's pretty constant. But towards the end of the flight, we did start drifting south a little bit, and this would have been the last time we would have crossed land. And here's some images that we took. So this is the Tarantula Nebula. These are some images that we took early on in the flight to test everything, to make sure that we can actually get good images. This is the Tarantula Nebula that we took. This is the Sombrero Galaxy, aptly named. I'm sure you can understand why. There's the M83 Southern Pinwheel Galaxy. This is only mostly just visible from the southern hemisphere. And then this is Abell 2345. This is a galaxy cluster. So you can see different spiral galaxies in there, a bunch of different galaxies dispersed around. Some of them are foreground galaxies, which are the galaxies in the galaxy cluster. Some of them are background galaxies, which are lensed as well. And I'll leave this on for a couple of seconds, but if you want to see more images, you can follow us on Instagram. Our Instagram handle is superbit.telescope, and we occasionally post a bunch of stuff over there, and more images as well, as we're processing and we're learning more as well. So why SuperBIT? Why did we do that, and what's the benefit over Hubble? As we all know, Hubble is coming up for decommissioning, and although this is not a very definitive thing, that SuperBIT is not scheduled to be a replacement for Hubble, but that is essentially the question that we're asking, and we're testing for that. So Hubble cost about $15 billion over the years since its launch and deployment to now. $15 billion to operate and maintain. SuperBIT was roughly 5 to 10 to maybe 10, but around $5 to $10 million. That's nearly 3,000 times cheaper than Hubble. And we're above 99.7% of the atmosphere. So we're essentially going to space for cheaper. And we can build 3 SuperBITs every year for the next 1,000 years, and we still wouldn't get to the cost of one Hubble. With SuperBIT, you also get the benefit of newer technology and the ability to upgrade on smaller timescales. So every year you can have a new SuperBIT go up because they're rated for 100 days. You can launch another SuperBIT, another one with newer and newer technology, better cameras, better communication technologies, especially more so better cameras, so we can actually image better. And it's easy to do improvements. There's no need to send astronauts. You can just send up another balloon. If one didn't work, that's fine. It didn't cost you $15 billion. It only cost you $5 million, which is still a lot of money, but compared to $15 billion, it's not that much. And redundancy planning is much easier. And that's one of the biggest reasons why SuperBIT was very cheap, was because we didn't have to plan for redundancy. If you are launching a $15 billion telescope, you want to ensure that if your main camera fails, then you have a backup. If certain wires fail, then you have backups. If certain power modules fail, you have backups for those. You want to ensure you have backups of backups as well. We did not have that same pressure on us. And Hubble is oversubscribed with science requests. Again, we're not saying we're replacing it, but what we're giving is an alternative if universities want to be able to study space, but not have to get in a line to actually get time from Hubble. You can actually come to SuperBIT, which is now not flying, but something of that sort. And I'll talk about what we're planning on for the future. And one more thing as well, we had a much larger field of view, 30 times larger than Hubble's. Of course, again, the fact that we did launch several decades after Hubble helps, because we have better technology, but that is in essence where we want to go as well. That is in essence where we want to head in this direction, with better and better technology as well. And just showcasing some images with SuperBIT versus Hubble, and I think both look beautiful. This is Hubble's image of pillars of creation, and showcasing the field of view, this is SuperBIT's image of field of the pillars of creation. So you can see that is how much Hubble was able to image, and this is how much we can see. And this is extremely important for weak lensing, because for weak lensing observations, Hubble is only able to see, and it can see very well, right in the center of the field of view. But outside of the field of view of Hubble, that is where SuperBIT can actually shine and get a lot of good images as well. And again, this is the antennae galaxies that Hubble took, great resolution right at the center. This is SuperBIT's version of the antennae galaxies. And this shows how much Hubble can see in one exposure versus how much we can see in one exposure as well. So our field of view is definitely much greater. And I briefly talked about this in the next steps, but what are the next steps? So the next one is a telescope called Gigabit, which we're still working on the naming for it. But this is, so SuperBIT was a pathfinder leading up to this mission. So Gigabit was a 1.34 meter, will be a 1.34 meter 3-mirror telescope with a gigapixel camera. So it's aiming to have resolution rivaling Hubble's, and with an 82 times greater field of view than Hubble, so even more than SuperBIT. And this will again be built in collaboration with U of T, Princeton, and Durham University, and this will be open to public scientists to also suggest targets, and it will also act like Hubble in scheduling. So what we're aiming to do is make this an observatory where scientists can actually say, hey, we want to image this, we want to image this. And there will be a lot more science use cases for Gigabit with its better resolution and its greater field of view. And if you're interested in watching a documentary, I'll leave this on for a quick little second as well, but you can go to documentary.superbit.space, and you can view a quick, I believe it's about 20 minutes or 25-minute long documentary on us building the telescope at our lab at the University of Toronto, right here in Toronto. It's a quick little documentary. It does include a bit of the launch, but it includes more about how we built it right here, and then we sent it over to Texas, to the NASA base in Texas to do the final integration and testing with NASA, and then we shipped it over to New Zealand. But this covers most of the Toronto portion. And then last but not the least, I'll show some fun images from our recovery. So zooming in to the previous images that I showed about the map, you see right here, there's our final resting point, and in Patagonia in Argentina. So this is very far south. If anybody has been to Argentina, you go to, we went to Buenos Aires, and then from Buenos Aires, it's a 3-hour flight south to a city called Comodoro Rivadavia. And then from there, and that I believe is right here, and from there it's a 12-hour drive south. And it was about 10 hours of that is without any signal, phone signals or anything, which is good, which is where we want something like this to land, because we don't want any person to be there. But for recoveries, it's kind of tough. So initially, what we also did in case we lost the telescope, we also had these data drop modules that I previously talked about. And this was a contingency plan in case we were going to land in water. So these are little drop modules that we tested. We dropped these over Argentina as well. And these are things that we can actually estimate to within about, I think it's about 100 meters, we can plan where they will fall depending on the winds as well. And these were dropped, and they were recovered by the Argentinian police. We told them about the locations over there. This is what they look like. We had NASA documentation on it, so people don't mistake it for bombs or anything. But the Argentinian police, we were able to coordinate with them, and they were able to recover these before we got there. And this is a picture of them actually recovering these. So this is one cool thing. And actually, Sky had a hand in building the release mechanisms for these, and a couple of other things. So we'll chat about that. In the past, SuperBIT has landed on its feet. So these are the test flights of SuperBIT, and a nominal landing. These landings can land on their feet. So they come down on a parachute, they land on the ground, the parachute disengages, and we get our telescope back. So this is actually SuperBIT. I believe this is one of the flights out of Texas with NASA. However, unfortunately, this time around, it was because of the winds. It was a little bit more because of the winds and the terrain, because it was a lot more hilly than Texas is. Um, Unfortunately, we were not able to recover a good lot of SuperBIT. However, we did recover every piece, just not in a functional format anymore. This is us out in the Argentinian Patagonian desert. This is what the terrain looked like. This right here is a portion of SuperBIT. This is our telescope, and then these are some solar panels that we collected. Which again, Sky actually helped design these solar panels. So you can actually see Sky is a very good engineer because the solar panels were intact, even though these metal beams were not, but the solar panels were. At least the squares of the solar panels were. And this is our space debris. But that concludes my presentation on SuperBIT and the benefits of SuperBIT, why we do astronomy from space. And if anyone of you would like to connect with me on LinkedIn, learn more about it later on as well, I'd be happy to chat about this more. Thanks for watching. And I'll go back right after this to something about SuperBIT. But I'll invite Sky again now as well.
All right. Thanks so much, Emaad. Really brought back a flood of memories listening to all of those SuperBIT facts that you were talking about. Very interesting, very informative. Gosh, I remember, a couple of years ago, back in 2021, I still remember first starting out, and you and the other grad students really put in a good pitch on our project. You showed this entire slide deck. It was a different slide deck at the time, but you guys whipped out this entire just incredible slide deck detailing the entire project, which instantly sold me, and was very excited to start working on it. So great to hear about all the amazing work that you've done and how successful of a mission that it was. And Emaad, I think you mentioned this, but some of the SuperBIT photos are actually out on the NASA Instagram too. So go and check those out.
Oh yeah, yeah. We did get featured on NASA's Instagram. We did get featured on NASA's blog, and also APOD, Astronomy Photo of the Day. We got one feature on there. I'm hoping we can make another one as well. We do need to launch and post more on those, but we did make APOD as well, which was a good feat for us. But yeah,
Yeah, geez, that's really awesome. And there's a SuperBIT Telescope Instagram account as well, right?
Yes, at superbit.telescope. I think I had that in the presentation as well. But I'm sure Victoria can put that in the chat as well for YouTube.
All right, for sure. So if anybody wants to visit any of those cool sites to check out the incredible work that has been done on this telescope, and I'm sure they'll be posting future events as well, future engagements with this telescope. And just to quickly wrap up this presentation, let's get back to it. Thanks again, Emaad. That was great.
No problem.
So we've come to the end of our presentation, and now we want to open up the floor to all of our participants. So I ask all of you watching, do you have any questions about the presentation or other comments, kudos, suggestions, any questions about Space Place, SuperBITs, any of that? In the meantime, I have a couple of questions to ask you, Emaad. So, Emaad, could you tell us, do you have a most frequently asked question or anything you kind of get asked a lot or most commonly about this telescope whenever you've done communication on it?
Yeah, there's a lot of different questions. The biggest one is, oh wow, you go up in a balloon. So like, how are you above? Because people usually don't imagine balloons to go really, really, really high. We know about birthday balloons. We know about slightly bigger balloons. They may go up high, but they're often very surprised about these balloons being able to fit a football stadium in them and being able to go as high as 110,000 feet up in the air. That's one big one, and then another big one is how we actually achieve the stability that we talk about and that I mentioned over here. And that comes down to the technology and the work that's been put in place by previous grad students, by engineering PhDs as well, and a lot of other people.
Mhm, mhm. Cool stuff. Got another follow-up question here, sort of about your history and your background. So, what made you choose to pursue this project in your grad studies? What sort of drew you to this specific project?
Oh, that's a good one. So I've always been very interested in space. I've been very curious about space, and I always wanted to learn more about it. That's why in my undergrad, my first major was math, but then my second major was physics and astrophysics, and I did a bunch of research projects in it. So I was really wanted to be hands-on with something in space. And I think maybe Sky, you know that same feeling as well. It's just
Mhm,
really fun to do something that is going to be up in space. So, so when I applied for grad school, I really wanted to do something more experimental rather than theoretical, and this lab was the perfect fit. They offered a lot of travel opportunity, which is something I really love. But then also they offered the opportunity to work with NASA on this project, which was essentially something I would have never imagined. And
mhm,
this was perfect. This was a perfect fit. And I was able to use the strengths that I had more so on the programming and coding side uh, to actually help with this mission.
mhm. Yeah, as you were mentioning, just the feeling of having something up in space. I feel like, I can definitely relate to that. Just, or just being able to do either the engineering or the science behind a mission like this just gives one such a sense of fulfillment. And I feel like sort of gives us the satisfaction of feeling like we're at the forefront of helping answer some of humanity's biggest questions about who we are, where we come from, why we're here, all those age-old questions that, in many cases lie somewhere deep in the universe. Um, so yeah, thanks, Emaad.
Yeah. Yeah, and
Um,
then I have a question for you as well, then Sky. On that note, how do
mhm,
you feel after SuperBIT's flight? Because I know so just for everybody out there as well, it was 2021. Yeah, it was 2021
yeah,
summer. And we did have the opportunity to come in person some days of the week. And it was kind of refreshing with COVID around us as well, although we did have to take precautions.
yes,
But it was kind of
definitely.
refreshing to actually see people. And
Mhm.
how do you feel given that SuperBIT actually flew? And just for everybody out there, so Sky worked on designing the solar panels, which the people who had to actually put it together were uh,
They didn't
were
like it
not
so
happy
much.
with. No, because Sky made it very rigorous to put it together with how many rivets was it?
Oh, I don't even remember, but there were so many rivets. It took a lot of riveting for every frame. So I'm surprised, but also not very surprised that they ended up
I think
staying
somebody
so
got
intact.
carpal tunnel. I think somebody got carpal tunnel syndrome. I'm joking. No one
Oh
did, but
no.
no one did. But no, but they did stay intact, which is what we needed. We needed something robust enough to actually go over, to actually fly. But how do you
Yeah.
feel given that SuperBIT flew?
Yeah, I followed the entire thing. Just something that I wanted to say about the SuperBIT project was, it was my first big opportunity in the space industry and in space academia. And so it really opened my eyes into how a space mission works, into all of the work from multiple disciplines that it takes to actually organize structure and build something as incredible as this telescope. And I feel like it just reaffirmed my confidence in the fact that I was pursuing the right path. And so that just really inspired me to keep pushing forward. I remember, doing some of the circuitry behind the telescope and staying several hours in the lab soldering, and it was just, by the end of it, it was just the most fulfilling thing to actually test the circuit, to see it worked, to go and cat up that solar array, do all the calculations, and make sure that it was robust enough to stay intact, and indeed it was. And also, I'd say there was an incredible sense of community. There were, you, Emaad, and all of the other grad students, and Bart, our professor. Everybody, there was just such a sense of community. Everybody was there to help each other. I remember we'd have lunchtime debates where Dr. Netterfield, Bart, and one of the grad students, or even more, would occasionally start debating some really intellectual topic, and then the rest of us would all just kind of sit around and eat our lunch, and it would be our entertainment for the lunch hour. So
yeah, we wouldn't get any work done during lunch. Well, not even during lunch. Lunch plus a few hours, I should say.
yeah, there you go. But I was just so glad it came together, and I just have so much appreciation for the mentors that I had and the team members that actually went there, saw it go up. So yeah, and thanks guys for allowing me to be a part of this project.
Oh yeah, and thank you for helping along with it. And you're completely right. Like, this is the cool thing about working on something like this, that it is so end to end, that you have to look at. I can plan for example, okay, this is how. For example, I can say stuff like, okay, you know what? We need to regulate the temperature of the telescope, or we need to regulate the temperature of our science camera. I can say that, but then I actually need to do that. So how am I going to do that? I need to worry about every single thing. I need to worry about things that are only relevant in space. For example, cosmic ray hits. I need to worry about those. I need to worry about radiation affecting different electronic components, affecting our telescope itself, the heat from the sun, because we're above the atmosphere, so we see big changes in the heat as well. So it's so end to end, which is really cool.
Yes, it is really amazing. And yeah, it was it's a high profile mission, but at the same time, it was small and tangible enough for us to really be able to get our hands dirty and really be actively involved with building and testing and being around the telescope, and just getting really hands-on with it, which was such a great opportunity. And just seeing everything sort of come together, that was really cool.
I agree.
Any undergrads in science or engineering, just who might be interested in this telescope, in doing a part of maybe the future gigabit telescope for your undergrad research position, please reach out to the team, because I'm sure they'd be happy to to check out the new generation of undergrads who are interested. And one other question as well, Emaad, just having talked to you and seeing some of the recent articles about you, I just wanted to highlight, you seem to have some really cool future goals. So would you want to share those as well? Just what are your sort of ultimate goals going forward?
Yeah, definitely. So I think space industry is where I really want to be in. Um, I'm sure you know, Sky, that it's what I find really cool, and what a lot of people also find really cool, and it's really fun working within the space industry and actually being able to progress the space industry. But I'm also looking to it more from a space tech perspective. So I want to help advance space technology. Now that could entail hardware, but also software. So how do we communicate with things that are in space? I help design the file downlinking algorithm for SuperBIT. I help with a lot of the communication side on the communication side of SuperBIT and a lot on the flight code as well. So I'm hoping to progress that side. On top of that, I'm also hoping to work with actual space hardware. Yes, you can have all the software, but you actually need something up in space as well. There's so much to progress. It isn't something that's it's only something that's going to be more up and coming. And slowly and steadily, countries and companies are looking to space. They're looking to invest in space as well, and I think that's a path where I want to go as well. So that's probably what I'm looking at in terms of the future.
Mhm, mhm. Very cool, very cool. Well, if you ever end up in space, hopefully we both end up in space, and
I think
we
you'll
can be.
probably end up in space before me. So please remember that. Please remember me. I'll trust me. I would love to come up there. That's actually one of my hopes as well.
Yes,
Eventually, it'll be kind of cool to see
that'll
this
be.
and then do another space place presentation from up in whatever version of the ISS there will be in the future. That would actually be a very cool thing.
Maybe it'll be Gateway.
Whichever one it is. Or we might even be standing on, yeah, we might even be standing on Mars. Who knows?
Yeah, well, a lot can happen in the span of a few years, so who knows? Um,
I 100% agree.
yeah. Okay, well that's terrific. Let me just check the chat to see some other questions. Wow, looks like we have a lot of questions from the audience
All
as
right.
well. So,
All right.
from Henry, how long will SuperBIT be able to stay in space?
So I'll clarify one thing. Space, we say near space. I like to say near space. Space doesn't really have a boundary. I mean, there are boundaries that are defined by different people. There are different lines that you define, but I would say near space or the stratosphere to be more accurate. But going back to the actual question, how long will it stay? So the balloons are rated for about 100 days. We This flight was about 40 days, but it was a healthy balloon. The only reason why we had to terminate was because we were going to go over Antarctica, unfortunately. And that would have meant we would not have been able to charge the telescope. We need day and night cycles, which is why we launched from New Zealand, not Antarctica. And with Antarctic flights, it's either you get a lot of day, or you get a lot of night. So what we did instead was we launched from New Zealand. So we are scheduled to get about 100 days. We're tested, or the balloon is rated, I should say. We haven't yet tested. They haven't yet tested 100 days, but it is rated for about 100 days. And that is the hope as NASA matures the balloon technology, that they can get about 100 days out of the balloon. Maybe even more if they can rate it for even more. But for now, it is about 100 days.
Another question from Nicole. What novel technology does SuperBIT possess to be able to deal with weak lensing? Is it the stability?
It's stability and also our optics, our camera, our telescope itself, and also the stability, and also the fact that we're up in the atmosphere. So with weak lensing, it is a weak signal. So we need to ensure that we can actually detect that signal. We don't have pollution. We need to ensure that we don't have pollution effects, or we can mitigate pollution effects. We need to ensure that there's not a lot of noise in our optics or in our camera as well. Different cameras have different level of noise that can distort images. So when we see those weak distortions in galaxies, we need to be able to actually see them and not mix them into the noise. So the stability is a big one because we need to ensure that we're stable enough and not moving. But then we also ensure that our optics and our cameras, our camera technology is also state of the art, so we can actually see and detect those little changes, and we have the resolution to be able to see them.
All right. Another question from Sophia. What procedures do you use, or are there any safety mechanisms in place to safely bring the balloon down?
So the biggest one, first of all, is being able to predict where it is going to land and ensuring that it will land well enough and clear enough of humans. So any cities, any places where there might be humans. For example, the place where we landed, it was 10 hours deep into a no signal area. So we ensured that it was away, away, away from humans. We did not even see a single human. While we were out there for about 20 hours, we didn't see a single car. Actually, there was one car, but that was early on in our journey over there. So we did see them. So that is one big safety rule, if you will. The other one is we use parachutes. So there's two sets of parachutes, two parachutes. One is for the telescope itself. One is for the balloon. So the balloon and the telescope, they separate and they both land separately. And once they land, then the telescope, once the telescope lands, for example, or the payload, the parachute disengages so that the telescope can land where it is.
Okay. Very cool, very cool. Another question as well. We have a lot of questions here.
All right.
You've made quite an impact. We have a question from Tom, and he says, so what's next for SuperBIT, or I guess in this case, Gigabit? Will they have any new instruments, or are any old ones salvageable and useful?
So for SuperBIT itself, that was the end. Unfortunately, SuperBIT did die after this flight. So there will be no more SuperBIT. However, like I mentioned, there is Gigabit. We've actually started the planning for Gigabit. And we're hoping to do test flights very soon, and then even a science flight within the next couple of years. So that is the next step for SuperBIT. In terms of salvaging old stuff, unfortunately, we're not able to. Well, we wouldn't do that for a lot of the things that we had. Even with electronics as well, we're looking to start brand new and fresh with better electronics. So we're not looking to salvage some of the old stuff. And in some other talks that I've given, and some other grad students and other members of the team that have given, what we've done is we've brought some of that space junk that we can say, went to space or near space and came back down. We've given that away. So if this was in person, we would have given that away as well. But that's what we're doing with the salvage that we recovered. For some of it, not all of it. Some of it we may actually keep just to test stuff, to test the effects of radiation up in the stratosphere as well. So different use cases, but we're looking at Gigabit now.
Maybe keeping some as mementos as well, trophies from the previous missions.
Oh yeah, we'll have a museum in our lab.
Yep. Remember that. I remember that. All right. I think we have time for one or two more questions. So from Victoria, how many balloon-borne telescopes are operating these days?
0. There are other experiments that happen, so they're not necessarily telescopes, but they may be scanning for something else. Occasionally they do them around December actually there is one that is currently flying, I believe, if I'm not mistaken. That flew from Antarctica. So there's missions that happen in Antarctica. There's missions that do not require a day-night cycle, but then there's also missions that happen in New Zealand that require a day-night cycle. So 0 from New Zealand at this moment in time, although they may be preparing. But then they did launch from Antarctica. They did launch one from Antarctica, which may still be up. It's called Gusto, if you want to look into that. And that's a NASA mission.
Okay. Next question is from Peter. To what extent did the balloon block the view of objects you would have liked to image?
Zero. If you saw the image of how the telescope is in the gondola, if we actually move it to a position where the balloon would actually be affecting us, we would be hitting the top. So because we're so far away from the balloon. Yes, the balloon is massive, but we're not directly under the balloon. We're actually way further south of the balloon. So our field of view is well clear of the balloon.
Okay. From Arvint, what operating environment conditions have you considered during the design and manufacturing of the telescope?
So if you mean by where we will be operating and preparing for that, so essentially preparing for the stratosphere, we've done there was radiation testing done. The benefit of having a professor and having professors in the collaboration who've done projects like this is they know which electronic components work and which don't. And there's very minute things that we also need to factor in. For example, hard drives. We did not want to use hard drives, and we had to use SSDs, for example. And why SSDs? Because hard drives vibrate. They're spinning disks. So we need to make sure that we have no vibrating components or any components that actually contribute to more movement. So things like that, we had to think about things like that. We shield everything. We had mylar, aluminized mylar on our telescope, which you might have seen. That's the silvery stuff on the telescope itself. We ensured that we did testing. We learned from previous missions as well that our professors have done. We learned from the engineering test missions too on what works, what doesn't, what literally gets fried by day-night cycles. And it's just a big testing process. And we learn from this, and then we give this to other people who are doing stuff. So for example, with Starlink, we did it for the first time. We failed after 10 days. We have a guess as to what certain component failed. And like I mentioned, Gusto, which is currently up, they have had Starlink for a month now, and they're enjoying that. So we're learning as we go from this.
As I've sort of continued to learn more about the space industry, seems like quite a bit of that is, is learning from failure, as you're saying. There's so much about space and near space that is so unpredictable and hostile, and that we still don't have a super good grasp on. So it was very interesting
I agree. And one of the things that we never even knew, because nobody's done a flight so far south, was one day we were taking images, and in our whole imaging code, after an image is taken, then we also check to see if the image is good or not based on certain parameters. We quickly see, okay, is this image good? Is this image bad? Is this image good? Is this image bad? And one of the parameters is how bright the image is. So we saw one night that we consistently got failed good images. Every image was being tagged as a bad image. We checked why, and it turns out that every image was very, very bright. And this was a funny one. So that same day, I was actually in New Zealand. When I was in New Zealand, I remember looking outside, and at that time they actually had an aurora over there in southern New Zealand. So I went out and actually saw the aurora, and it was really cool. I came back and I learned, oh wow, every single image is really bright. And we're like, okay, are we being obstructed by balloon lights or something like that? Is something causing the brightness? Turns out there's an aurora, and we never even knew about that. We did know about it, but we never even factored that in. But it was really cool to actually see, okay, wow, that can actually be a big factor. So it's stuff like this that we learn as we go.
That's very interesting. Never would have thought that would even be a possibility, but guess it happened.
Yeah.
Well, thanks so much, Emaad, for answering all the questions. We still have some more, but probably best that we just wrap it up here because we are nearing the end. So let me just share my screen again. All right. So again, Emaad, thank you for your amazing talk and for coming here today and sharing with us your experience and your knowledge and insights. So as we wrap up today,
thank you for the invitation.
Yeah, thank you again. And so as we wrap up our presentation today, I want to tell you to check out our website, spaceplacecanada.ca, often to make sure you don't miss what's new, especially to stay in the know about the upcoming solar eclipse and how to get our nifty Space Place eclipse glasses. And again, more details and events relating to that coming soon. Also, be sure to follow us on social media, Instagram, X, Facebook, and LinkedIn, or you can subscribe to our YouTube channel right now. And as I said before, I would encourage all participants today to get involved. Email us to inquire about our work, be a volunteer, or apply to be a member. We're engaged in advocacy and planning, recruitment, events, and fundraising. So if you're looking to get involved, there's an area for you. And just as a final heads up, with a donation of $40, we will send you our awesome and unique planetarium music card. And with a donation of $75 and your mailing address in North America, we will send you the music card and a copy of Bob McDonald's An Earthling's Guide to Outer Space. And so if you do plan to donate and would like some of this swag, when donating, please indicate in the Write a Private Message to Us box on Canada Helps. And that consider donating to the Canada Helps link, and that's going to be posted. It's going to be posted in this video. And so this is a very special offer for those of you joining us tonight. Thank you again for joining us today. It's been a real pleasure to learn and discover more about the exploration of our universe with such an enthusiastic and thought-provoking community. If you liked today's event, please give us a thumbs up and make sure to subscribe for more information on events like these, where we can deepen our knowledge together in a community setting.